I think you can directly then share your screen. You don't need any permission for that. So let me, you can check it now. Yes, we can see your slides. So let me first introduce Professor Lanza. We are very happy that he accepted to participate in the second emerge school. Professor Lanza will speak about hybrid 2D CMOS microchips. He will show us his group activities on integrating 2D materials with conventional CMOS electronics and systems, presenting activities mainly using memoristic devices, using 2D materials, and targeting applications such as data storage, computation, neuromorphic computation, encryption, and communication. So a few words about the Professor Mario Lanza. He is Associate Professor in Material Science and Engineering at the King Abdullah University of Science and Technology in Saudi Arabia. He has published over 200 research articles in top journals, including Nature, Science, Nature Electronics, among many others. He has received multiple top distinctions like the IEEE Fellow, the Young 1000 Talent Award, the Marie Curie Fellow, while he is a distinguished lecturer from the Electron Device Society of the United States of America. And he is editor-in-chief of the Journal of Microelectronic Engineering. He serves in the board of many other journals and international conferences. So, Professor Mario Lanza, we are very happy that you participate in our school, and the floor is yours. Thank you very much.
Thank you very much. Can you hear me well? Okay, perfect.
Yes.
So it's really a great pleasure to present my work in front of so many excellent people, and I'm going to talk mainly about our recent work on hybrid 2D CMOS microchips. And this is the outline that I will follow during the presentation. This is a relatively new field, and therefore I'm going to make a good introduction to review nearly all the papers that are out there. So you can have a global idea of the whole topic and its perspective. Then I will show our previous results on hexagonal boron nitride-based membristors fabricated on traditional silicon dioxide substrates, which is the substrate that probably many of you use during your daily experiments. And then I will show you our recent work, which is, it basically consists on integrating the 2D material device. Instead of the silicon oxide substrate, we put it on a CMOS microchip, because we think we don't need to reinvent things. If there are things that are there and work well, then we can go and try to combine them to get the benefit from each of them. And finally, I will show you what are our next steps and also the challenges to overcome. So probably you have already studied about two-dimensional materials. You already know they are atomically thin. And here you can see a cross-section, a top view TEM image of one two-dimensional material. In this case, is hexagonal boron nitride, which is like graphene, but made of boron and nitrogen atoms, so it's insulating. Here you see a top view image of a bilayer. You can see that now these hexagons cannot be seen so well. There is some AV stacking. And this is a cross-sectional view of a multi-layer. Okay, you will see that I work with insulating two-dimensional material, which is multi-layer hexagonal boron nitride. So because it's insulating, I need multi-layer. Otherwise, if it is only one layer, normally this has it's more difficult to apply, because for the insulator, we need to block the electrical current. So if there is only one layer, there is quantum tunneling effect. So normally we work with a little bit thicker materials, and this is how it looks like. Probably you know that two-dimensional materials have many amazing properties. Here I summarize some of the properties that are applicable to graphene, like giant electromobility, excellent mechanical properties, and very high thermal conductivity. This is also shared by other two-dimensional materials. It has also good magnetic properties and high transparency. The important thing from an electrical point of view is that you have two-dimensional materials with different band gaps and different conductivities, and therefore, using this family, you can fabricate electronic devices because you have all what you need: conducting, semiconducting, and insulating. So these materials can be fabricated in many different ways. The first method that was presented was the mechanical exfoliation of small crystal powder, but this is something that is not scalable. If we want to employ them for, let's say, real-world application, we have two methods. One is liquid phase exfoliation and then spin coating or deposited with some different methods. But that leads to thick stacks of flakes with random orientations. So for high integration density, it's not practical because this film can contain several very high amounts of defects. For some applications, they will be okay, but for ultra-scale devices, it's very different. So the method that is preferred by the semiconductors industry when working with 2D materials is chemical vapor deposition. It consists on a heating chamber, normally a tube where one substrate is placed. Then there is a precursor and a carrier gas. And then by opening some valves, these two things can be introduced in the chamber, and at high temperature, after some time, the material can be grown. And this is some SEM images of the sample during the growth process. First, you have the deposition of some seeds, then they start to grow laterally at high temperature until they merge, and then we have a continuous film. And this is something that has been demonstrated by many different authors. Most labs have a little tube with a diameter of 1 inch, 2 inch, 3 inch. But this can also be done at the wafer scale. This is a machine that is being commercialized by Axtron, where you can put here one 300 millimeter wafer, and it has a shower head technology where the flow of gas is homogeneous, and therefore the homogeneity of the film that you grow is also more homogeneous. So the question that we have to do to make ourselves is, okay, where can we use these 2D materials inside the structure of a modern microchip? So here you have the cross-sectional TM image of a modern microchip. You know that it's modern because it has the recent back power delivery scheme, which is can be observed by this big metallic pads that are separated by insulating material. And here on the top, we have the routing connection. So basically, the semiconductor is only this part. Normally, we call it silicon, semiconductor industry, silicon technologies, but the silicon part is only this. The rest is conducting and insulating material. Okay, so where can we put the 2D material here? The first approach that many people is trying to do is to use semiconducting 2D materials to replace silicon. Here you see a cross-sectional TM image of a silicon transistor with the source, drain, and the gate, and here you see the bulk silicon. If you zoom in here, what you observe here, the silicon lattice is almost perfect with the silicon dioxide layer, insulating layer, and the top gate. And this works very well. However, when you make the device very small, you start to have leakage current towards the substrate and horizontal phonon scattering and also short channel effects. And the idea is that if we can make a transistor with this channel is atomically thin, we will have better electrostatic control over all the channel, and therefore we may end up with better performance. And here you can see a cross-sectional TM image of one prototype that has been fabricated by IMEC with a gate length of 224 nanometer. And this idea sounds very good. However, the problem is that, in fact, these materials can have some impurities and some defects, like lattice distortions. Also, if you need to do the transfer, you're going to have also probably contaminants from the substrate and from the PMMA that you used for the transfer. Also, the transfer may produce cracks, so this may reduce yield. Also, in fact, the metal evaporation also can produce some damage into the 2D material. And basically, we have observed that there is a high source drain contact resistance and a bad interface with the gate dielectric. Nevertheless, several people has managed to fabricate relatively large transistors using this approach with gate lengths normally higher than 1 micrometer. And they show some reproducibility. However, look what happened when you try to make the devices very small. Here, the typical characteristic from the device, which is the sub-threshold swing, is degrade a lot. You always have a hero device, but in fact, when you test many devices, the properties are degrade from one device to another a lot. In fact, this not only happens with the sub-threshold sweep, but also with other parameters like the on-state current and the threshold voltage. You can also check this paper from IMEC, which is done by one of my former PhD students who did the postdoc there, and she observed similar things. So making the devices small is very difficult. But also, moreover, something that you may not see in many studies is how the characteristics of the device evolve over time when you try to switch on and off the device for many times. And here you can see a couple of results when we measure thousands of IV curves in the same device. This is a backgated graphene field effect transistor with dielectric aluminum oxide. This is the same when we use boron nitride. It's a little bit better, but still there is some variability. And this has to be considered, and almost nobody studied this. We study this. If you are interested in this topic about the yield reliability, variability, and stability of this kind of 2D materials-based transistors, you can also check the work from Professor Tibor Grasser, who is a very big expert in this field. Here I leave you one representative paper. So another different approach is to not to grow the material directly on the wafer, but to integrate it at the back end of line of one microchip that has been already prefabricated. And this has the problem that because we grow the 2D material at high temperature, we cannot grow the material directly on the microchip. So we need to grow it on an independent substrate and then transfer it on our microchip. So this was done for the first time by IBM in 2014. They fabricated a graphene radio receiver in which basically everything was made of silicon technologies, but the channel of the 3 transistors in the circuit was made of graphene. And they observed an increase of performance of a factor 10 compared to a similar circuit using silicon transistors. So this was a big improvement. This is another study, quite similar. They also transfer monolayer graphene on a CMOS readout circuit. And in this case, is for being used as a conductive path with this S shape in a circuit that is for an optoelectronic application, is for a camera. And here the graphene covers an area of 100 micrometers square. In the previous example, the channel of the transistor is 10.8 micrometers square. Both cases, it worked well. However, this is low integration density. These are not very small devices, they are big devices. There are other examples, more recent. This is a paper very recently published in which the authors fabricate biosensors transferring graphene on a pre-patterned silicon microchip. You see here the graphene plays the role of conductive paths between these 2 wires where it can be functionalized to detect different kind of biochemical species. And here the area of the graphene is also quite large. So this is also low integration density. This image is an image from a microchip that we designed in the 2D pilot line from the European government, in which we can fabricate some graphene field effect transistors. This is also using graphene transfer on top, and then you can pattern. And the minimum feature size that it can be patterned is 5 micrometers. So this is also not very high integration density, although here we managed to make different kinds of transistors. Because all this is based on the transfer, I have to comment on the transfer. So the transfer is something that there are many academics and many researchers that are very reluctant to believe on it. I want to stick to the facts, which is that in the past few years, IMEC has made big progress on the transfer of monolayer two-dimensional materials. Here you can see some images and, more importantly, some characteristics of different transistors that have been fabricated with wafer scale transfer. In IMEC, they use this wafer debonding method. Let me just mention something. They are doing here monolayers. As I mentioned at the beginning, I use an insulating material, and therefore I have to work with multi-layers. And with multi-layers, the multi-layer is not so, it does not crack so easily. So basically, it's much easier to transfer. There is another different approach for those who don't believe on transfers that has been recently reported by a group in MIT, which basically they design a silicon wafer, and then they grow the 2D material directly on it. But as I mentioned, this cannot be done at high temperatures. So what they do is they have a CVD system with a zone that is at 250 degrees, which is a temperature that the transistors can survive. And it has another zone with 550. And therefore, they manage to make the reaction in the high temperature zone and deposit the material on the wafer that is on the lower temperature zone. And using this approach, the authors fabricate an SRAM cell with 4 CMOS transistors and 2 MOS2 transistors. I did not understand very well what is the motivation of this type of cell. I guess it's just a proof of concept. They demonstrate significant currents, but these currents are patterned in very large devices with 68 micrometers square of area. And in fact, the current density is 10,000 times lower than the state of the art for molybdenum disulfide transistors. So basically, it's a nice proof of concept, but there is a lot of improvements to do in this method. And actually, because this temperature is 550, I'm also a little bit skeptical to see how they can reach the target mobilities required by the roadmaps. So anyway, it's an interesting approach that I wanted to mention. And then here comes to the introduction of my work, which is that we in my group, we are starting now to work on transistors, but traditionally we have worked with memristors. So let me mention the main difference. In the transistor, the current that flows between source and drain flows homogeneously along the whole 2D materials-based channel. But in the memristor does not work like this. The memristor consists on a top electrode, bottom electrode that are separated by an insulating material. And then when we apply electrical field between both of them, we can trigger a dielectric breakdown, similar like a lightning in a storm between the clouds and the ground. And this triggers the low resistive state. And when we reverse the polarity of this electrical field, we can partially distort, partially disrupt this filament and trigger a high resistive state. You can see that the breakdown only takes place in one specific point of the sample, okay? This is a local phenomenon that in fact is called weakest link phenomenon. It only takes place at the electrically weakest location of the sample. So basically, if you have here some wrinkles, some PMMA, which are more insulating locations, the dielectric breakdown will never take place there. So the dielectric breakdown will always take place in a completely clean location that probably contains also some local defects in the insulating material. Another important point is that the materials that are used for state-of-the-art memristors are bad dielectrics, which means that they contain several native defects. For example, state-of-the-art memristors use metal oxides like hafnium dioxide or tantalum oxide, and these materials are not very good dielectric materials. In fact, the good dielectric is silicon oxide grown by thermal oxidation of silicon. That is a very good material that shows a very high energy to break down, and therefore when it breaks, it does not recover. These materials contain many defects. The dielectric breakdown takes place at lower energies, and therefore it can be recovered, the breakdown. So This is also an advantage because if we have two-dimensional materials that contain some amounts of defects, they may not be suitable for being used in transistors, but they may be used in memristors. Let's say that the memristor tolerates much better local defects than the transistor, and therefore they can be applied. So when you use the memristor, normally you switch it between the low resistive state and the high resistive state for thousands of cycles. But at the end, it normally happens that this conductive filament propagates laterally and it cannot be recovered anymore. And if it cannot be recovered anymore, you end up with a permanent low resistive state, which is what you see here. The device has failed. So our idea of using a two-dimensional material grown by CVD is that it contains some local defect. You see some areas are perfectly layered, but some others look more like almost amorphous. The layer regions are very stable and you need a very high energy to form defects. But the amorphous regions, you can form defects much more easily. So basically, you have a material that is where it's easy to make defects that is confined in a nanoscale volume in between another where it is very difficult to make defects. And this, according to our initial idea, could make a confinement effect, and therefore maybe we can extend the life of this type of devices. So let me show you how we started in this field. The structures that we fabricate are metal, boron nitride, metal. But first, we start with multi-layer hexagonal boron nitride produced by mechanical exfoliation. You can see the little flake here. It has almost perfect layer structure. And here you can see the sandwich structure. We measure many, many devices with many different thicknesses, and we observe something very similar. Low leakage current that, of course, for thinner samples, it increases the leakage current. We show a dielectric breakdown. The electrical field is almost constant around 12 electrovolts. Its breakdown voltage follows a trend. However, in this material, because it has no defects, when we trigger the dielectric breakdown, it's a dielectric breakdown that is a very hard process and completely breaks the device. However, our devices, the ones that switch well, are made with CVD grown multi-layer hexagonal boron nitride. And this is a sample that looks like this. This is the optical microscope picture where you can see the boron nitride on the polycrystalline copper foil. If you take SEM here, you see something like this. You see that the surface of the sample is rough, and there are almost no wrinkles because when you put the 2D material on a rougher substrate, the compressive strain that forms the wrinkles can be mitigated better, and we observe less wrinkles. The topography of the sample is rough because the copper substrate is rough. However, when we scan the surface of this sample with the conductive AFM, applying a very low voltage, we observe no pinhole, no signal of current, which means that the layer is continuous and it has no pinholes. Actually, you can observe it better in the cross-sectional TEM images. Here you see that the layer is continuous. Of course, there are regions where the material looks better layer, others looks worse layer. And you can see here that almost everywhere you see a lot of local defects, and also almost everywhere you find layer locations. This is the type of material that we want for our device. We repeat the conductive AFM scans, but now we apply a higher electrical field. And what we observe is a picture like this. We observe many locations that are insulating and show no current. However, we observe also some isolated conductive spots. These conductive spots mean basically because we apply the same voltage to the whole image. So basically, these are electrically weak locations. And this picture look very, very similar to the typical picture you observe if you measure a metal oxide used in memristors, like hafnium oxide. So when we saw this, the first thing that we thought is this material is a candidate for exhibiting resistive switching. We made also with the conductive FM another electrical test, which basically consists on applying a constant voltage at the insulating location and inside of one of these conductive spots. For the same voltage, in one of these insulating locations, we just observe electrical noise. However, when we put the tip in one of these electrically weaker locations, we observe that the currents for the same voltage, the currents are much higher, and we also observe random transitions between two levels. This is a phenomenon called random telegraph noise that is related to the trapping and detrapping of charges in this location. So basically, this is also one symptom that takes place that could indicate the presence of resistive switching in the material. Okay, the materials that normally show resistive switching, they also show this phenomenon. So this really encourages us to go ahead and fabricate the devices. And we do the fabrication like this. We fabricate 25 micrometer square gold, boron nitride gold on silicon oxide. You can see the sample. We make the first lithography to pattern the bottom electrode, transfer the boron nitride, another lithography to make the top electrode, and another lithography to open a hole on the bottom electrode so that we have a good electrical contact. Then we apply here. You can also see the top USCM image with the wrinkles here of the device and the bottom electrode and the top electrode. The wrinkles confirm that there is boron nitride in it. We measure several devices, and this is what we observe. Low leakage current followed by dielectric breakdown. And after that, we observe, we apply a current limitation of 1 microamp. And after that, if we apply a reverse voltage, we observe that the current is reduced. And then if we apply a subsequent positive ramp, we observe a dielectric breakdown again, this time at lower voltages than here. And this can be repeated cyclically for hundreds of cycles. And basically, this is the confirmation that this device exhibits non-volatile bipolar resistive switching, okay? With the set and the reset events very clearly here. And we repeat the experiments in many different devices with different sizes, and we observe similar behavior. These are all for the same size. We observe similar current levels and similar switching voltages for most of the devices. Let me also mention that this is when we use multi-layer hexagonal boron nitride with a thickness between 6 and 8 nanometers. When we repeat the same process using monolayer hexagonal boron nitride, we observe that most of our devices, like 95%, are shorted and only 5% work well. So, of course, this can be improved, and there are some groups that have tried monolayer hexagonal boron nitride as dielectric, and they observe higher yield than us, which means that they are better in terms of fabrication than us. However, still with multi-layer, using the same process, with multi-layer, you can get much higher yield for memristive application. Regarding the switching mechanism, we have made cross-sectional TM images in stress devices, and we observe that the layer boron nitride looks contaminated by particles coming from the metallic electrodes. Actually, if we heavily stress the devices, we can observe clearly the formation of gold filament inside the boron nitride. We also fabricate devices with different top electrodes, and we apply electrical field and observe that the speed for breakdown depends on the diffusivity of the metal used. So basically, this is also one indication that what forms the filament is metal penetration into the boron nitride. So until here, we were very happy. Everything worked well. We published our results in Nature Electronics. We were all happy. And then the next step, we wanted to fabricate smaller devices and larger circuits. So we fabricate with electron beam lithography 320 by 420 nanometer devices in an array of 100 by 100 wires. So this is like 10 kilobit array. And we tested, here you see only one part of the array because the array is big. And then we tested the devices again with the same protocol. And we observed something interesting. We also apply a current limitation. In this case, we apply 1 microamp because these devices are small. We apply the positive ramp, and then we observe the dielectric breakdown. However, during the reverse ramp, we observe that the current increases orders of magnitude above the current limitation. This did not happen before. For the big devices, we observe that they increase a little bit, maybe maximum a factor of 10, 1 order of magnitude above the current limitation. But here is like 3 orders of magnitude, okay? So after that, we observe that there is no resetting, okay? There is no reset. And this is something that shock us because it happens randomly in around 50% of the devices. And then we were a little bit confused, like why this happens? Because in the other devices, the devices that don't show this overshoot phenomenon, where the back ramp shows currents of the same order than the current limitation, we always observe the reset, okay? So what is the reason? The reason is that this current limitation is introduced through the semiconductor parameter analyzer. And this system has a delay of around 70 microseconds. And 70 microseconds is enough for having 1 peak of current here, which you cannot see, but is there, and breaks our device, okay? This happens randomly, but also even in these devices where it did not happen in the first cycle, maybe this happens in the next cycle. So basically the conclusion is that for our 25 micrometer square devices, as you see here, all the devices work well. But for the small devices, most of the devices fail in the first cycle, and the ones that don't first in the first cycle, they fail very quickly in the next cycle. So nothing works, basically. And then we were very upset, but let's understand why this happened. If you have a resistive switching material, this material has a random distribution of defects. When you have a very big device, you have high probability of catching defects. And for the small device, you have a low probability of catching defects, okay? The key is that in our devices, the resistive switching is based on the filament, and the filament is formed in the locations that there are defects. If you have defects, you are triggering the breakdown at low electrical field and forming one small filament that can be easily reverted. But in the small device without defects, look what happened. When you go small in size, the breakdown field increases a lot for all devices, for all materials. And therefore, the energy to breakdown is higher and the size of the filament is higher. And therefore, this thing does not switches back, and it stays in a permanent low resistive state as you see here, okay? That's the reason why the small devices don't work. Then we think, okay, how to solve this problem of the delay of the semiconductor parameter analyzer, or let's say of the delay of the current limitation. And we see how the industry does. And this is the way in which most professors in the universities fabricate membristors, mainly with this common bottom electrode structure using a shadow mask, which is the worst method possible. Using lithography, like we do, okay? You can make a cross point or a crossbar, but this does not have the current limitation. What the companies do is to integrate the resistive switching material on a microchip like this. Here, if you make a cross section, you can see the front end transistors, and here in the back end of line interconnections, you can see that they have titanium nitride in the middle. They have the half-new oxide. Okay, they have integrated the membristive material at the back end of it. Then the transistor provides 3 advantages. The first one is the transistor is the current limitation element, and the maximum current that it gives is defined by the gate voltage. There is no way of having a current peak because it's defined by the channel conductor. The second is that if we switch off the voltage in the gate, and you can basically mitigate all the current across the memristor. So basically, you are mitigating sneak path currents in the from one device to another in the crossbar array structure. And the third advantage is that in the microchips, the bottom electrode, this thing here, first is very small, and second is very stable. So this is a big advantage to fabricate very small resistive switching devices. So then we fabricate some CMOS wafers, 300 millimeter with 180 nanometer CMOS technology in a foundry. And then we terminated the wafers in the last metallization layer, okay? We did not passivate the wafers. Then we cut the wafers. We cut each microchip, as you can see here. And this microchip contains many test structures. But here in this region, we have some 3 test structures that we use. The first one is 2 pads with a bottom electrode and top electrode. So here there is no transistor. Second is a transistor in which the drain contact is not patterned. And the third one is a crossbar array of 5 by 5 transistors in which the drain contact is not patterned. Okay. So basically what we do is we transfer the boron nitride here on the surface, and then we pattern the electrodes. Okay, you can see here, we have transferred the boron nitride and we pattern the top electrode. This electrode. And then here the same, and here the same. You can see the difference here. Okay. And here you see the long wrinkles proving the continuity of the 2D material. Of course, there may be some micro cracks here. Okay, this is something to be considered. But in general, it's a very long and continuous film because it's multi-layer. It's 6 nanometers, so we can transfer big areas. And the big advantage is that now we can adjust the material that we want, and we can have a very small device size of 0.056 micrometers square. So as you see in the introduction part, all the previous attempts were very large device size. The smallest size that I showed was 10.8 micrometers square. Here is really sizes that are similar to those in commercial membristic devices. Some tricks about the fabrication. The wafer, as we extracted it from the factory, it comes with native oxide. It needs to be removed to expose the vias before transferring the boron nitride and patterning the top electrodes. Okay, and then what you have is the transistor that is connected through all the metal layers to the surface. And here in the surface, we transfer the boron nitride, and then we have the boron nitride and the top electrode. Then we have a device that now is 0.053 micrometers square with structure gold, titanium, HBN, tungsten, which is the material of the via. Then we measure the standalone device without any transistor. We observe random fluctuations on the conductivity, but there is no reproducible switching. And if we increase the voltage beyond 2.5 volts, basically what we see is that the device melts, okay? There is no current limitation. So basically, this device is so small that probably contains a low amount of defects, and the energy to break down is higher, and therefore it makes that this thing melts. When we measure the standalone CMOS transistor, it works as expected, as it should. Like one transistor, there is no secret here. And then we measure the one transistor, one memristor cell with gate voltage 1.1 volt. And then we observe that during the first IV curve, which is the blue one here, we observe the current increases. And during the back ramp, we observe that there is an increase of current for the same voltage. So the resistance has changed. Now we have a low resistive state. And then when we apply a negative ramp, we observe that the conductivity decreases, and we observe a current level that is similar to before. So basically, this thing is showing non-volatile bipolar resistive switching. But now is different than the case before in the large devices. Why? Because first, we don't have, first of all, the resistance of each state is very high. The currents are much smaller than in the big device. Second, in the big device, we had sharp transitions, and here the transitions are quite progressive. So basically, these two factors are telling us that I don't think we are working in a filamentary mode. I think we are introducing some defects, but not producing the complete breakdown of the boron nitride. Although there may be people who may disagree, okay? This is a first study on the microchip, and we are doing more studies to try to confirm what is the switching mechanism. But from our point of view, we don't think this is filamentary. Okay, we repeat this in many devices, and you can see that it is reproducible. But the shape of the IV curves is not really perfect in all cases. In some cases, it's much uglier, but in fact, we don't care about this too much because in real applications, the devices are stressed with pulses. So we stress the devices with sequences of pulses like read, write, read, erase, read, write, read, erase, etc. And we measure the current. And what we observe is that, as you can see, we can, if you see only the reads before and after the write and the erase events, we can see clearly high resistance, low resistance, high resistance, low resistance. So basically, this is confirming the non-volatile bipolar resistive switching by applying pulses. For 3 different types of electrodes, we have 3 different switching voltages. Here, we need to apply almost 4 volts. Here, almost 5.5. But for silver, we have switching that is at almost CMOS compatible voltages. And actually, for this type of electrode, we also observe quite decent switching energy and switching time. It's not world record, but it's quite decent. For a first approach with this technology, I think it's a good indication. The most surprising thing for us was the endurance. Because, you know, in such small devices, it's very difficult to get very high endurance. If you check in the literature, you will find many papers that show high endurance. But most of them are in large devices, where it's much easier because you have much larger amount of defects. And this is a defect-enabled switching mechanism. Our devices are very small. We still see 1.5 millions of cycles. Well, in fact, it's 2.5. Here, you can see that we can also adjust the on-off ratio in different ways. Here, I show you the plot for adjusting the on-off ratio by changing the duration of the write pulse. But you can also adjust it by changing the duration of the write pulse and also the switching voltage. And we compare with the works in the literature, and we found very few studies in small devices that show high endurance. Very few, very few. And this is one of them. So we were actually quite happy because these endurances and the size are similar to those in commercial devices. You see, these are ReRAM memories from Fujitsu made on with metal oxides, and they promise 500,000 cycles, not more. And the phase change memories from Intel, well, the ones that they offered before, now they stopped the production, they offer 10 million cycles. So this is quite similar, and what we are doing now is to try to measure many more devices to make some statistics. Let me also say that when we reduce the gate voltage, we can also observe threshold time resistive switching and spike time independent plasticity. It's not the nicest spike time independent plasticity in the world, but we have made fittings and also an electrical model with a SPICE and also system level simulation of a spiking neural network. And we observe quite decent performance for this type of devices. So I think this is something remarkable, especially because it's achieved on a microchip, and this already has a relatively high technology readiness level compared to many other articles that report resistive switching devices on silicon oxide. So finally, let me briefly mention other things that we are doing now. We take advantage of some internal interconnections in the microchips to try to build some logic gates, and this is what we did, and we demonstrated a couple of logic gates. However, these microchips were not designed by my group. They were designed by our collaborators. So basically, we are now trying to redesign the microchips to make some structures that are more suitable for our intended application. Another thing that we are trying to do is vector matrix multiplication. This is very important operation for artificial neural networks because artificial neural networks work doing intensively vector matrix multiplication. We characterize our samples in a board like this. And we have tested it with 1 kilobit, so 32 by 32 crossbar array of gold boron nitride gold devices, the size is 25 micrometers square. So it's the old samples. And here we don't have the transistor. So basically, this sample does not work well. It has a lot of sneak path currents. But we detected one region of the crossbar without sneak path currents that works well. And in this region, we have made a decent 16 by 8 vector matrix multiplication. And the degree of error that we get between the hardware vector matrix multiplication and the software-based vector matrix multiplication is very small. And more importantly, the errors are systematic. They are related to the electrical noise of the board at low currents and also to these saturation ranges, the saturation of the current in different ranges. This is why this point here deviates, but this can be corrected easily. And we also try to switch the devices in an analog way. We managed to do it. However, the on-off ratio in this case is much lower. We are now redesigning some microchips. This is a microchip we have done in TSMC. And this is the layout where we include the crossbar and we include different type of test structures for memristive applications. And here we also include one circuit, which is the one that you can see here, that is for true random number generation. And actually, we have employed the boron nitride memristor for true random number generation, and they work successfully. We have done it using an Arduino microcontroller. However, we want to do it on the microchip, integrating the 2D material here. We are working on this. And finally, let me mention about the main problem that we have, which is in my group, we are not growing the boron nitride. We get boron nitride from commercial sources and also from other collaborators. And sometimes from our collaborators, we get good samples. However, when the student graduates or the postdoc leaves, getting more samples is difficult with the same quality. And when we buy samples from commercial sources, we have the problem that even if, I mean, the manufacturers say some nominal values in the website, but the reality is that we buy the samples and they are all different. So basically, when we open one of these boxes, we fabricate the devices based on the thickness and the number of defects. We optimize the size and the material of the electrodes and the electrical fields that we need to apply. And we do all the work, but when we open another box, we have to do everything again. So it's really, really time consuming and expensive. So what we are doing now to solve this problem is we got some samples from the company Eichstron. They fabricate the machine to do the boron nitride at the wafer scale. They are capable of fabricating samples with always the same value. And this is very, very useful for us because now when we fabricate the memristors, we observe similar properties in all of them from one batch to another. And now is when we can really go and make optimizations. Before was like a little bit playing lottery. You don't know which kind of boron nitride you're going to get. Now we are really making big advantage and fine adjusting the properties of the device. So as a conclusion, I will say that CVD grown 2D materials still contain too many defects produced during the growth or during post-processing, and they are hindering the performance of the devices, especially in the transistors. However, you can still fabricate memristors with these 2D materials because you don't need such a high crystal quality, and the memristors tolerate some densities of defect. So we have fabricated the first hybrid 2D CMOS microchip with high integration density, and we have fabricated 0.053 micrometer square memristors with high endurance above 1 million. And we are now integrating 2D materials on CMOS microchip for other applications, including true random number generation and vector matrix multiplication. If you are interested in our work, you can see our publications. You can also see I sent in the chat before a message saying that we have positions available. If you want to apply for a postdoc in my group, you can do it through the platform Web of Talents. I put the link in the chat. And finally, I would like to thank all the students in my group and the postdocs for their very hard work during the past few years. And that's everything until now. I will be happy to handle questions if you have any comment. Thank you very much.
Thank you very much, Professor Lanza, for this very nice talk, very impressive one, and all these papers that we published last year. I think there are some questions in the chat already. Let me check. One question from Mr. Abbas. Did you try to identify the role of defects in boron nitride, their role on your device performance?
Sorry, is it written here in the chat?
Yes,
or?
it's the first one.
Okay. You try to identify the role of defects in HVN on your device performance. I mean, yes, because we know that without defects it does not switch, and with defects it switch. And the performance of the device depends on different parameters. The first one is the thickness of the boron nitride. Second one is the amount of defects. Third one is the lateral size of the device. And the third one is the chemical composition of the adjacent metallic electrodes, okay? With these four things, you can adjust the properties of the devices and the resistance of the states and the switching voltages. However, we could not make a systematic study because we don't get reproducible quality of boron nitride over different batches. We are now starting to do this with the new samples from Eichstrom. But I will say that we have managed to make memristors almost from every boron nitride by adjusting these four parameters.
Okay, I think also the second question is about the thickness of boron nitride on the device switching. I think you already described that when you decrease the thickness, you have lower yield, in my understanding.
Yes. Yeah, because for when you go smaller in thickness, the transfer is more complex, you get more cracks, more pinholes, and then the yield is lower. Moreover, the devices that work with thinner material, they are going to show higher currents, which is also not desirable. You want to have a high resistance to reduce the energy consumption. At the same time, if you use too thick boron nitride, maybe you need to apply too much energy to switch it, and then you trigger a permanent breakdown. So it's a compromise of all these parameters. I will say what works well for me is thicknesses between 6 and 8 nanometers. However, if the material has a lot of defects, it may also work, even if it is thicker. So it's a combination of these four parameters.
Another part of the applicant question is about if you measure any quantum effect while you scale down the thickness, if it is predicted something to be observed when you go down to a few nanometers?
Yes, we have observed in some devices conductance quantization. And we have a paper, I think it's in NPJ 2D Materials and Applications. This analysis was done by one of my collaborators, Professor Juan Bautista Roldán from University of Granada. I think he observed in some devices the typical jumps from different conductance states, and he made all this kind of fittings.
At which temperature? Room temperature?
Yeah, room temperature. Actually, conductance quantization in memristors has been also observed in other metal oxides, and it happens at room temperature. Not sure. I mean, basically what happens is that the current is a multiple of the quantum conductance, and it changes between multiples of the quantum conductance, which is the conductance of a perfect column of one single atom in the memristor. However, that is something that I don't look so much. There are many groups who like to discuss about the switching mechanism. I think the switching mechanism is very, very difficult. Even in metal oxides, people talk about movement of oxygen vacancies, and people still don't know where the oxygen vacancies go. Some people say they form an oxygen reservoir. Some people say no. And this does not have a very good contrast in the TEM image. I mean, it's very, very difficult. We have tried all the methods. So I am more practical. I go more looking for performance. If it switches, I don't care so much why it switches as far as it switches. Of course, I want to understand how the device switches, but I will not defend my switching mechanism. And if you don't agree with my proposal of the switching mechanism, I will feel happy because this is a debate we should have. So, to be honest, I don't deal so much with these quantum things.
Okay, thank you very much. Another question about the fabrication techniques that you use to build your memory store devices. So if these techniques are compatible with standard CMOS processes
Yeah.
or are special fabrication techniques required for memory stores
No, no,
using
no.
good materials.
This works very well for this completely compatible with the industry because this you can see here in this slide, you can see an industrial memory store. Okay, this is metal oxide on the microchip. Okay, the only difference in our case is that we transfer boron nitride, and boron nitride it is grown on a different substrate. It is transferred at the wafer. It can be transferred at the wafer scale with the process being used by IMEC, for example. And then the bottom electrode, you can put the bottom electrode that you want. And sorry, at the top electrode, you can put the top electrode that you want. So it is completely compatible. The boron nitride can be grown at the wafer scale with the machines that I have shown. It's a CMOS compatible temperature transfer process. So there is nothing that avoids you from doing. We have used gold, we have used titanium, we have used silver. One of the reviewers of our Nature paper was very annoying, saying, "No, but you use gold. This is not CMOS compatible material." We use gold because it's the one that allows us to switch best. We cannot use titanium nitride because titanium nitride requires a special recipe to have a very good conductivity. There are not many works in the academia using titanium nitride. But in fact, this is integrated at the last metallization layer. So in fact, there are papers on patents of other devices that use even iridium, which is even more contaminant in the backend of it. Because this is not so close from the transistor, even gold here will be fine. Of course, will not contaminate the microchip, but will contaminate the chamber. But I mean, you can use it also, and it works as we demonstrated. But yes, everything, you can use another different material more friendly, like aluminum, copper. But yes, it's completely CMOS compatible.
Okay, so before I check another question about replacing gold, for example, with silver, and the applicant was wondering if you have similar switching behavior using silver. And I'm going to add also that we are working here in HMU on perovskite memory stores. We use silver because silver participates in the switching mechanism. Actually, we have this migration of silver that assists in the filament formation. So have you tried similar device with some silver instead of gold?
Yeah, we have tried in all cases. We have tried in the very early. We see with the silver, it switches very, very quickly. And the same happened here. With the silver here, it switches at much lower voltages. This is related to the much higher diffusivity of silver. That is something known and very well. It became popular after the Nature Materials paper from Professor Joshua Young's group, and many people use it in the field of perovskites. People use it because it does not switch based on intrinsic species. Let's say like a metal oxide, it switches more based on metal migration. And silver is the metal that migrates the best across anything. So yes, we have tried silver, we know. And actually, for this very small device, the switching that we observe, even with silver, is non-volatile bipolar. But if you go to big areas, what you observe is threshold type switching because the filament dissolves. But here is so small that you need to, even with silver, you need to input more energy because there are less defects. And therefore, it becomes more, let's say, non-volatile. But in the big devices, it is volatile.
Okay, thank you very much. So if there is not any other question, let's thank again Professor Lanza for this very nice webinar.
Thank you so much.
Nice to meet you. And let's proceed to the final speaker for today. we had some change in the program regarding the speaker, but this, of course, is from the same institution, the same company. We have together Eduardo Lopez Larraz from Big
Hello.
Brain. Hi. Just a few words. Let me tell a few words about our speaker. So, Dr. Eduardo Lopez Larraz will speak about the digital neurotherapeutics nanotechnology for everybody, anytime and everywhere. Dr. Larraz now works as a research scientist at Big Brain. It's a company in Spain. His work lies at the intersection between engineering and neuroscience, and aims at developing neurotechnologies that improve the quality of life for people. During his career, he has focused on investigating machine learning, signal processing, and statistical methods applied to the field of neural engineering, with a special emphasis on neurohabilitation for patients with motor disability. So thank you very much for your participation. I will give you the floor now. Thank you very much.
Thank you.
You can share your screen directly.
Yeah, I will.
At the bottom is a share screen button.
Screen 2.
Great.
Okay, can you see my screen now?
Yes, we can see full screen. Thank you very much.
Okay, perfect. Thank you very much for inviting me. It is a pleasure for me. As Konstantinos was saying, my name is Eduardo Lopez Larraz. I am a neuroengineer and I work as a research scientist in BitBrain in the neuroscience department of the company. And today I will be giving probably a different talk to the others that you have listened to today. So my talk will be more focused on applications of electronics. So it will be more applied talk than technical talk. And we will be discussing about how digital neurotherapeutics can help society in the next future. Okay, so as I was saying before, I come from a company that is called BitBrain. We are located in Zaragoza, a medium-sized city in the north of Spain. And the company BitBrain started as a startup from the University of Zaragoza. So by the year 2003, Professor Javier Mínguez, who couldn't join us today, established his professorship and started his research line in robotics and neurorobotics. So the laboratory there became the first brain-computer interface department or laboratory in Spain. And like most brain-computer interface departments, by those years, it started in the field of robotics. So Professor Mínguez started in autonomous navigation and these kind of applications of robotics. And some years later, he started investigating about how neural interfaces or neurotechnology could combine with robotics to produce solutions that can impact society. So in this laboratory, the second wheelchair controlled with brain activity was presented. So I can show you here a video of how this was validated. This was year 2008. And it was the first time that continuous control for brain continuous control for an automatic wheelchair was provided. So it was through a paradigm called P300, in which a 3D environment was created in front of the participant, and the participant should focus his mind or her mind into the place he wanted to move. And this intention by these colored stimulations was decoded through some electrodes placed on the head. And with this, the robotic system that controlled the wheelchair could move to the place that the participant wanted to move. Right? So this was one of the most cited brain-controlled robots papers. There were many magazines worldwide describing this this kind of works. And one of the most recurrent questions that came to the laboratory in those years was questions from journalists, from stakeholders, from the society. One of the most common questions was, when is this kind of technology going to impact society? Like, you are controlling a wheelchair with the brain. This is like a bulky system. How far is it from society, from helping someone? Like, a wheelchair like this for people with mobility problems can be very helpful, but these systems are not easy to transfer. Like, who is able to buy a system like this? Who is able to place electrodes, do the maintenance of a wheelchair like this? How is this? How can we transfer this technology to society, right? So after thinking a lot and considering how to continue these research lines, in the 10 years after the first research was conducted at the university, by 2012, 2013, Professor Minguez founded BitBrain, whose dream was to bring neurotechnology closer to society. So at the beginning, the first works were as, can you see my cursor? I have to do this, right? Yeah. So in this left panel, you see the type of experiments that were done at the university with many electrodes on the head, on the muscles, to try to capture as much information as possible from the brain, from the muscles. And this, for instance, is an example recorded at the University of Tübingen by our team, in which a stroke patient, which could not move this arm, was being monitored with brain and muscle electrodes, so that we could create a system that decodes the patient's intentions, patient will to move, to train a system that could be used for his or her rehabilitation. So then a system was trained, and then the patient was attached to a robot, a rehabilitation robot that could move the arm of the patient. And when the system, through all these electrodes, decoded that the patient wanted to move, then the robot would move. So these are strategies that require intense hardware, intense signal processing and AI, a large piece of research on biomarkers and how to optimize treatments. And all this was done in this first decade of the 2000s. But then after 2010, 2012, the paradigm kind of changed, and we started to focus on how to transfer all this technology to home, to society, to enable people to do this kind of recordings at home. So it has been a long path to try to optimize systems, to miniaturize components, to see what we can get rid of and what is mandatory. But not only that, like all this work is not just a technical work, but we had to work on the regulation of all these technologies, safety to keep patients' integrity safe first, ethics, many discussions with stakeholders. But during this second decade, we believe that we have come a step closer, that we are having technology that is kind of easy to use at home, while keeping a precision that is similar to clinical systems. Okay, so now starting 2020, 2023, we are happy with the technologies that we have, and we believe that we can start now with the clinical trials that will validate all these technologies to give the green light to start commercializing them as neurotherapeutics, which I will be showing more in detail now. So So here in BitBrain, we're a team of 60 people. More or less, a bit more than half of us are engineers and scientists. These 60 people have been with organic growth, so we only have the money from our business plus from R&D public projects. So we work on many research projects funded by Spanish or European funding programs. And we focus on creating neurotechnology, doing the whole pipeline. So we do our own hardware, we do our own software, we have our AI engineers, and we even run our clinical trials, our research trials to validate our technology. Okay, so many times when we start showing and explaining people what neurotechnology is, and making like my mother or my grandma understand what neurotechnology is, it becomes a bit complicated for people who are not familiar with this field, right? Like when I ask someone completely naive in that field what they think neurotechnology is, they imagine like something weird, a brain, cables, technology, very complicated. But in the end, neurotechnology is not as complex as it could seem. Right? In the end, neurotechnology is some type of technology that interacts with the nervous system, with the central nervous system, which is brain and spinal cord, or with the peripheral nervous system. Right? So nerve stimulation, muscle stimulation can also be neurotechnology. So there are many examples that seem complicated, like wheelchairs, as I was showing before, or these first systems presented by Professor Birbaumer in 1999 of the very first person with ALS, completely paralyzed, producing a text with his mind. Some brain implants that are becoming super popular now with Elon Musk's Neuralink and other initiatives as these, spinal implants. But also the truth is that neurotechnology is more common than one could think and has been with us for many years, for many more years than I've been alive. So first examples of neurotechnologies could be the pacemaker, which comes from the 1950s. Also, we have cochlear implants. Many people, you walk in the street, maybe some of the people in the audience has a cochlear implant. More recent, from the 90s, we have deep brain stimulation for applications as Parkinson's. So people have an implant in their brain that stimulates constantly to reduce their tremor. And even more recent, we have retinal implants. So all these are implantable examples of neurotechnologies, but we also have non-invasive, non-implantable, right? So let me go back to the topic of my talk, that is digital neurotherapeutics, and let me introduce the concept as it is, right? So what are digital neurotherapeutics? So these are solutions or tools that try to prevent, treat, and manage health conditions, brain health conditions, right? So instead of just going to your doctor and having a one-to-one appointment with him or with her, we can have technological solutions that help this doctor to prevent diseases, to treat diseases, or to manage and follow up these diseases. So why is this so helpful, or how can this change the world? Well, the main limitations that these one-to-one appointments with the doctor have is that it limits time, space, and individual reach to each patient, right? So you need to go to the doctor, you need time to go there, you need to move to a place. It is very different on every place of the world, but in the region of Spain where we are located, I said before, we are in a city called Zaragoza, and it belongs to a region that is called Aragon, that only the big city, Zaragoza, has decent hospitals. So there are people who live in the Pyrenees, these high mountains that can be located 2-3 hours away from the hospital. And of course, if you have an accident, you have a small hospital closer. But if you need an MRI, a scanner, a follow-up of your Parkinson's, you need to go to the big city in many cases, right? So these limitations require some solutions that are not always easy from a resources point of view. So it is very difficult to have a specialized neurologist in dementia on every small village or every small area that covers a few villages. So these technologies, these digital neurotherapeutics, constitute a solution that can be very helpful there. So I was saying before that digital neurotherapeutics at its core are created with software and AI. So at the core of digital neurotherapeutics, we have software. An important piece in there is artificial intelligence, which is becoming more and more popular, and like almost everyone nowadays has heard about AI, deep learning, deep neural networks that are used for different applications. But health is one of the applications where this AI solutions are going to be more impacted, right? So software is the core, peripherals are hardware are the peripherals. What does this mean? That if we have a system that can receive information from a patient, decode this information, and produce a piece of information for the specialist, a diagnostic, we can do this with different type of hardware. We can measure this information with different type of hardware. So we have some electrodes today that allow us to measure some information, but in 10 years, the electrodes will be much better and will allow us to capture much better information. But the core of all of it will be still the software and the AI. And it will allow us to retrain and to improve these systems while we improve our hardware, our peripherals. So these peripherals are as we do with computers. We have mouses, we have headphones, we have different keyboards that we can change them, we can improve them, we can have some new hardware that gives us different functionalities. And that's what we build, for instance, at BitBrain. So we are specialists in creating non-invasive brain monitoring systems, basically EEG or electroencephalography, and we can do that with different approaches. Okay, so first here on top we have a cup-like EEG. This is like a swimming cup that includes some electrodes that spread around the head. Typically, you use 16 or 32 electrodes, and you can configure a system like this for many different applications. You can set more electrodes on the frontal areas or on the back, the occipital areas, and this allows you to understand, to investigate how the brain works in its different areas. This type of technology has traditionally been used with some conductive gel to improve the impedance between the skin and the electrode. And this is what has been the state of the art since the 1930s till 10 years ago, right? So 10 years ago, or a bit, like obviously a bit before, but when it started being established was in the 2010s or so, where dry systems, optimized and minimalistic EEG systems like this were created. So a system like this does not need gel, conductive gel, does not need any conductive solution to interface between the head and the electrode. And these systems, the advantage that they have is that they have been optimized for specific applications. So a case like this has 6 or 9 electrodes placed in the motor areas of the brain. So the electrodes are located to measure, for instance, when a patient is trying to move his hand or his leg to control, for instance, a robotic system that allows in his or her rehabilitation, right? So this has been a reality for the last 10 years or so. And what we have been working on in the last 5 years was going a step forward, a step beyond. And these kind of systems are still a bit expensive for many applications and are still a bit complicated to use. So usability has also been a key step here. For instance, I can tell you this is a system that we have optimized here at BitBrain, and that was created in the framework of a neurorehabilitation project for stroke, for people who have half of their body paralyzed. So we created this system so that a person with only one functional hand could set himself or herself the headset autonomously. So only using one of your hands, you can play the system, you can adjust, make little adjustments, and see that the signal is being recorded properly. But still, these systems are still a bit expensive for particular use. And we thought, how can we improve this kind of technology? And a natural solution that came is, okay, textiles and garments is something that is with us, is super natural. We wear them all the time. It is actually an industry that is much more developed than other industries, like fabrication of metallic electrodes is more expensive and more complicated than textile manufacturing. So we thought, let's see how we can integrate textile electrodes and conductive textiles into EEG system. We knew that conductive textiles are a thing for many years already, but the problem that we had here is that the signals that we are monitoring, the electroencephalography, has a very worse signal-to-noise ratio than other biosignals that are recorded sometimes. So, for instance, we knew that electrocardiography was done easily with conductive textiles, but with in our very first tests, we saw that EEG was not as easy. So the signal-to-noise ratio that we were getting was poor. It was very difficult for us to keep good conductivity or to lower impedances. So it took us like 2-3 years of tests, testing materials, testing different configurations, trying to minimize interferences due to sweat or perspiration. But in the end, we created a prototype that was built exclusively with conductive textiles, either for electrode and for data transmission. And then we attached an amplifier, like the ones that we have been using for other electroencephalography systems. So we have, as I was saying, we have been trying to improve the way we monitor brain activity. So we have been developing solutions that reduce the need of electrolytic substances to improve conductivity. So we passed from gel-based to water-based to dry systems. And then, as I was saying, then the last step was using textiles. So we have been working hard on understanding how much we are losing for using these simplified versions of the technology. So we published a couple of papers in Frontiers showing how passing from gel-based to dry systems, we don't lose that much information. And we recently published a new one showing that textile EEG provides us very, very similar results to what we already had with dry systems. So we conducted a study with 10 participants comparing the brain activity that we were measuring with eyes open, eyes closed, also when they were trying to move to replicate these rehabilitation paradigms that I was mentioning before. We also analyzed how the impedances vary between wet systems, dry, and textile. And we saw that, and we were aware that textile or conductive textiles have much worse impedances, which means that we can have under unfavorable circumstances, we would have worse recordings. But we could see that in good cases, when the person is stable and relaxed, we have exactly the same signal-to-noise ratio. So we can measure the same type of activity than with a standard system. But when the person starts moving, we, of course, have worse signal quality, which means we can use these textile systems for some applications. And for others, we still need to work on, for instance, artificial intelligence solutions to try to minimize these contaminations. So this is the technology that we ended up developing. It includes these 5 electrodes on the forehead, plus 2 electrodes that come on the upper part of the ear. This is the first time that this solution is integrated and validated. And it will allow to measure in very different circumstances without the need to go into a laboratory or to a clinical setup. So let me see. I don't know if the audio of the video will be shared. Can you confirm if you hear it?
No sound.
No sound? Oh, okay, it's a pity. So it is an 11-year-old kid explaining how he is going to set up the system to himself, right? So I was telling people that, okay, we all know that kids nowadays are very familiar with technology in general. You give a kid a phone and he or she will easily learn how to use it. But this kind of technology that we are developing here is a bit particular. So it is not showing a kid how to play with a phone or control a TV or something like that. We are talking about technology that can be used for diagnostics. We are talking about technology that has been designed according to medical regulation, and that can help doctors improve their diagnostics. So making technology that we can be satisfied and we can rely that a kid would use himself or herself is an important milestone. And we focused on optimizing not only the technology itself, the electrodes, the transmission, but we needed to improve the usability, because our objective in the framework of neurotherapeutics is that anyone without previous technology knowledge can use this technology at home in a reliable manner. So if you give it to a person, a young or an old person, and the result that you get after measuring the brain can be misleading and can be to a bad diagnostic, that would be horrible, because it would even increase the burden of the specialist. So we want something that helps the specialist to diagnose better or monitor better. So there was a huge effort here in terms of usability to create a system that is easy to place and has instructions so that a 10-year-old kid or a 90-year-old person can set up autonomously. Okay, let me change a bit. I have been talking about the hardware, about the components that I was saying before that we would use as peripherals. But let's go to a use case, to a particular use case. I don't know, probably many of you are not familiar with sleep medicine. So when you have a sleep problem or a respiratory problem like sleep apneas, this issue that you stop breathing during the night, you need to go to your doctor. You need to get a sleep test that is called polysomnography, in which all these sensors are attached to your body and are monitored during a night. So you go to your doctor, probably the doctor will say, okay, you will have a polysomnography study in 5 months, 6 months, whenever the waiting list allows it. And then you will sleep at a hospital laboratory, which is not very friendly. It's probably cold, it's not beautiful, it's not comfy. So you need to be there wearing all this. Then you will go home, and a specialist, a very well-trained doctor, will have to interpret the data that was recorded from all these sensors. So normally there is a process to score your sleep data, focusing on the EEG, scoring the sleep stages that you went through. So you probably have heard of REM sleep, stage 1, deep sleep, light sleep. So the trained specialist will go window by window of your EEG recording. So EEG recordings are split on 30-second windows or epochs. And the specialist looks at them and says, okay, the person is awake here, or the person is on phase 1 or phase 2 or REM sleep. He does this for the whole night and creates what is called a hypnogram, which is what you see here. Okay, so these are the phases that the person went through during a night. And these, together with the interpretation of all the other biosensors, like the breathing sensors, movement sensors, is what the doctors use to support the diagnostics. Not only that, not only is complex because of how time-consuming it is, but there is also a problem of the subjectivity of this process. So there are studies demonstrating that when different experts analyze the same data, their agreement, their match, is only between 80 and 85%. Okay, so this was an incredibly good place to start using neurotherapeutics and artificial intelligence. And it is the first use case that we addressed here. So we took our textile EEG system that you see here, and we can record a person while he or she is sleeping. We follow the same procedure as an expert would do. We split the night recordings in 30-second epochs, and we pass them through a neural network. Okay, we had to create this network. We trained it with different databases, and what we get with that is a hypnogram similar to what the experts could get. So we got our system, our data set scored by experts and by our network, and we produce a report with different metrics. We can say, okay, this person has been half of the night in stable deep sleep, a quarter of the night on REM sleep. The sleep efficiency has been 80%. There have been some awakenings, all these kind of metrics that we can get simply in a couple of seconds after having a well-trained system. Okay, so systems like this started being published on papers in 2018. Like when I say being published, I mean reaching accuracy levels that matched the inter-expert agreement that I was mentioning before, that was between 80 and 85%. So there were some results in the previous decade using decision trees or some simpler classifiers that were a bit behind that. But since 2018 or so is when results were started to be positive enough so that they could be used or they could be integrated in products like this. So we proposed an architecture that was focusing on only frontal electrodes. So remember, we have this headband which has electrodes on the forehead, has these 5 electrodes around here. And we train our own deep learning architecture optimized on that. Apart from that, we recorded a data set with more than 100 participants. We invited them to our sleep laboratories, which are, let's say, nicer, cozier than a hospital room, a laboratory. And we measured them with a full PSG system, polysomnography system, as I was showing you before, with breathing systems, breathing sensors, movement sensors, EEG, muscle sensors, and also we included our headband, our technology. So we had like 2 data sets in one. On the one hand, we had a full PSG setup, and on the other hand, we had the headband system. We labeled all these data sets using the clinical standard procedures. So we sent it to external experts that scored the nights, produced the hypnograms that I was showing you before, and then we used those labels to train our deep learning architecture. And when we tested it with unseen data, we saw that we have an 87% of accuracy of creating the hypnogram with the polysomnography dataset, and an almost 86% with the textile system, right? So remember that I was telling you before that the agreement among experts is between 80 and 85, and we are surpassing this result with this deep learning-based system. So this is the first success case with this technology. And so how can we extend this? What are other applications where we can use digital neurotherapeutics? Okay, to give you some numbers, we know that from the WHO that around 60% of the population are suffering nowadays from brain disorders. So it is not just sleep disorders. There are many mental disorders like depression, epilepsy, Parkinson's, dementia, or other types of cognitive impairments, stroke, that, as I was saying before. So digital therapeutics, the major area, is progressing kind of fast nowadays, but the effort that is being placed on digital neurotherapeutics, so those therapeutics focused on the brain, is becoming massive in the last 5 years. So one more interesting number here, it was recently characterized that 1 out of 5 people aged 50 or above are already at some stage of cognitive decline, of a cognitive decline status. This means that, 20% of 50-year-old people will develop a cognitive decline in any stage of their life, right? So it is not as easy as saying a person has or does not have a cognitive impairment or a cognitive decline. So after investigating this a lot and working with experts, we see this process, this cognitive decline, as a continuum process. So we have people without any cognitive deficit, and we have people at the other side with very severe and disabling dementia. Okay, but in between, we have a process that is not very well characterized, that is very difficult to characterize and to monitor. And this is one of the areas where digital neurotherapeutics can impact society more in the next decade. And you will see why now. So I was saying we have healthy people, then we have people who start having some memory deficits, start realizing that are forgetting more and more where they put their keys, where if they put salt to the food or not. But then these people go to the doctor and they get some standard tests, and the tests say they're normal. They are not below the threshold. That means that you have a cognitive decline. So these are people that are called subjective cognitive decline. And that has been seen that they have a much higher risk of developing dementia due to Alzheimer's than people that do not go to the doctor complaining about this. So these are people that are a very important target population to be monitored. We also have people with mild cognitive impairment. It can be due to Alzheimer's or to any other disease. There's no clear agreement among experts, but some say 50% of the dementias are due to Alzheimer's, others will say 80% are Alzheimer's, but it is a very relevant number, the ones that are originated by Alzheimer's. That's why we split this into the two lines. And then once you get the dementia diagnostic, in the case of dementia, you have early dementia or mild dementia, medium dementia, and severe dementia. Same for other types of diseases. So it is very important to know and to characterize where a person is at all this continuum to see if we can anticipate decisions, if we can anticipate treatments. And it's very difficult to monitor these participants on daily clinical practice. As I was saying, if you are living 3 hours away from the hospital, it's very difficult to monitor you on a daily basis, right? So I'm gonna show you 3 studies that we are running right now at BitBrain in collaboration with our partners, targeting both the screening and diagnosis of people with cognitive decline and the treatment of people who are starting to suffer a small cognitive decline. So the first study is called Hogar, which means home in English. And this is a study whose objective is to monitor this process, this continuum of cognitive decline by using self-administered EEG technology at home. So here we are recruiting 500 elderly participants above 60, and we are choosing them at different stages of the process. So we are taking some people who are cognitively healthy. We're taking some people with subjective complaints who do not match clinical criteria to have cognitive impairment. We have some people with cognitive impairment, and we have some people with dementia already diagnosed, okay? And we are taking this heterogeneous population to have a cross-sectional study, so meaning that we can characterize people at different stages of the disease. But we also plan to have a longitudinal follow-up, meaning that we will follow them through 4, 5, 10 years, if possible, to see that if with the measurements that we do now, we can see who of them is progressing or worsening his or her condition. If we measure them now, we measure them in 10 years and see that this person has developed dementia, we can predict retrospectively which are the participants or which are the brain patterns that make us anticipate that this person is going to develop a dementia. So we are not only measuring the electroencephalography at home, but we are also doing a multi-domain assessment. So we are characterizing different cognitive domains like memory, attention, orientation, speech, and many others. We do like a 3-hour assessment to each of these participants divided in 2 days. And we are involving more than 20 medical doctors of different disciplines. So we have neurologists, geriatricians, pneumologists, physiologists, electrophysiologists. So they are helping us to recruit and establish all the parameters that we need to measure here. This is a study that started in January this year. So we only have 40 participants already out of the 500 that we are aiming at. But the results that we are getting with the recordings at home are more than 80% of recordings being successful, which is very important. Remember here that we have people that are not familiar with technology, not at all with neurotechnology. Many of them are above 80 years old, and they are being recorded just with the help of one relative. So if we have a person with cognitive decline, obviously it is very difficult for him or her to set up the technology, but it is only helped by his or her partner, a son or a daughter, something like that. So we don't have a clinician, an experimenter near to the participant. Let me try to play the video here. So the way we configure the system is very simple. We give them a headband like this that they can set up with the help of a tablet PC that we also give them. And they place the system and they go to sleep. So they sleep with the technology for 2 nights, and we will use the neural network that I was showing you before to understand the sleep patterns and other analysis to see how the brain patterns during sleep are correlated with their cognitive status. And we'll see. So during this 2024, we will be recording participants, and we will finish the cross-sectional study. And from 25 on, we will start the longitudinal study. Oops. Okay. So this study was only diagnostics, or it can be used for follow-up, but we can also do treatment with brain monitoring systems. So I will explain you 2 approaches for treatment of cognitive decline. The first one is done with the person awake. So this research comes from the 90s, where a professor in Austria found a biomarker that was related with the cognitive ability of a person. So there was a biomarker called the desynchronization of the individualized upper alpha rhythms in parietal and parieto-occipital regions, whatever this means, that this correlate when you had it larger, your cognitive ability was better. So first question, can we affect this correlate, and will it increase the cognitive ability of a person? So they started doing this with brain stimulation. So they artificially increased this brain parameter in a population of healthy participants, and they saw that the cognitive ability, especially attention and working memory, was improving in these participants. So this is like going to the gym. You train, you get better at something, and you have a better function. So with years of research, it was in the 2005, 2007 or so, where neurofeedback approaches for cognitive enhancement were proposed. So the idea here is very similar. We know that there is some brain pattern that when it is higher, it is correlated with a better cognitive ability. So we developed this system that tries to change that. So we have an elderly person here wearing our technology. We have the electroencephalography being monitored. Wait, give me a second. Okay, so the brain activity is monitored in real time, and the person is seeing a screen that is encoding this brain correlate that I was mentioning before. So we want this type of activity to become larger. And we code it, telling the participant, okay, we want you to turn this square into red for as much as possible. We cannot tell you how, we don't know what you have to do, but the more this square is in red color, the better. So the person needs to be looking for mental strategies, needs to be guiding their thoughts in a way that produces more positive reward. This is operant conditioning. You tell a person what needs to be done, how her brain needs to be, what's the status that her brain needs to reach. And the interesting fact here is that she's training like this for 30 minutes a day for some days a week. And the changes in her brain are not just happening while she's seeing the screen, but they persist after the session is over. They persist for some time after. Okay, so here we have the signal processing pipeline. We are computing the power of this headband that is individualized for each person. So an important point here is that one is not fitting all. We need to individualize the specific parameter of each person, and we encode this information, this individualized information, into this feedback. When the person is training for some time, we expect this brain correlate to be changed, and we expect this to result in a better cognitive ability. So this type of technique is not something that we have invented, of course. There is a lot of research behind. This is a meta-analysis of this type of intervention with studies for more than 10 years. There have been results showing how the cognitive ability increases, how the EEG or the brain patterns change with sessions. However, there are no studies yet showing if this is effective for people with cognitive decline. So this is the next step, obviously. We are engaged in trying to solve that question. We will try to have some results about that. We started already a study in which we expect to involve 30 people with mild cognitive impairment, and we will see if this results in an improvement of their memory and their cognitive ability. The very last study I'm going to explain is a similar thing, but we do it during sleep. Okay, so we don't need the attention of the person. It is better in the sense that the study before needed some effort from the person to modulate their mental status towards a desired space. Here, we have a different approach. It also comes from the neuroscience literature. So there were some studies in the early 2000s by Professor Jan Born in Tübingen showing a brain correlate that was related with better memory consolidation. So we have slow waves, which are a transmission of information between different brain regions. And we know that when these slow waves occur more frequently, a person will have a better consolidation of tasks or memories learned the day before. So this is again a case in which makes a lot of sense to try to exploit these solutions with people who are suffering cognitive deficits. So the literature here was showing us, and the work done by this Professor Born in 2013 was showing that artificially creating these slow waves led to improved memory consolidation during the night, right? So they were inducing these artificial waves. They were extending the sleep stage of deep sleep where memories are consolidating. So, and they were showing that this causes a behavioral improvement in memory. So this again is something that we tested here at our laboratory. So we have a person sleeping with our technology. We are monitoring the brain activity in real time throughout the night. And in this case, we have the AI that I was mentioning before that is analyzing the sleep stages. So we are monitoring if the person is awake, if the person is in light sleep, or when the person reaches deep sleep. When we know in real time that the person is in deep sleep, we know that these slow waves, these waves are happening, and we can stimulate them to produce more slow waves, which is what I was mentioning that is related to an increased consolidation. So we are here at the stage of deep sleep. The system is monitoring in real time, and here we see a slow wave has been detected in the stage of deep sleep, and this is the estimation of what the stimulation is going to do. So it sends 3 stimulations separated around 1 second, and it will create a train of slow waves that is supposed to extend this deep sleep phase. Again, there will be another one, and it sends these 3 stimulations. I didn't say it. The stimulations are done auditorily. So we send auditory tones that are loud enough for the brain to hear them and process them, but are not as loud as to wake the person up. So this is an unconscious process, but is modulating the brain itself. Okay. As before, we did not invent this. There is enough evidence. There are meta-analyses studying and reporting that this neurostimulation works. There are some recent studies also questioning this, and there are many researchers trying to understand who are the people who can benefit more with this type of intervention, because with elderly participants, apparently it becomes more difficult because they have altered brain patterns, they have smaller waves that are more difficult to detect and to stimulate. So this is an open research line that still requires some years of work, but we are starting to try to validate this also with people with cognitive impairment, and we expect to have some results about if this actually can help their memory consolidation in some time.
Just Eduardo, you're in conclusion part, okay.
Yes,
You have 2 minutes.
sorry.
Thank you.
Yeah, almost done. So just to give you some take-home messages about digital neurotherapeutics, we believe this is actually a potential solution that can help treat, manage, and prevent brain conditions. It will be helpful because it overcomes one of the most persistent limitations of current clinical practice and diagnostics, which are time, space, and the individual reach to the participants. An important message here is that these solutions will improve as technology improves. As I was saying before, we have passed from gel electrodes to textile electrodes, but who knows what comes next? So as the technology improves, we will have new applications and we will have solutions that can help even more and more people. So it's important, it's crucial to acknowledge the role of artificial intelligence here. So recording, like having technology like this that you can measure at home also enables you to record larger data sets that it was previously possible. So before you needed very well-trained people, you needed specialists, and you needed well-equipped laboratories, and now we can record the brain at home very easily. And finally, it is not only helping diagnostics, it is important to help guiding treatments. So it is very positive to help specialists to detect when a person is getting a cognitive decline, but it is a reality that now there are no effective treatments for people with cognitive decline, dementia, and this kind of mental problems. So improving treatments is something that, although experimental at this time, needs to be progressed and improved further to see if we can solve all these conditions. And that's it. I would like to thank all our team, all our funders. Obviously, there's a lot of work behind this, and there's a lot of public money helping us. So thank you, and thank you for your attention.
Thank you very much, Dr. Lopez Larraz. Very interesting talk. Very nice results. There are some questions in the chat. So one is about, thank you very much for the nice talk. Which kind of conductive textile have been used in the devices? Are these commercial textiles? Or?
Yes. We are not developing the threads ourselves, so we are buying. I could not tell you the specific materials, but we are using threads that are covered with silver alloys, and that's what we use to create our electrodes. So I told you before that we had a first prototype in which also the transmission from the electrode to the amplifier was done with conductive textiles. We tried that, but in the end we opted for having flexible PCBs for transmission and conductive textiles for electrodes. But I don't remember the materials.
Thank you very much.
Thank you.
Any other question, please write in the chat box, or you can speak directly. Meantime, I have a question about can you give us some numbers about the market potential of wearables for healthcare applications? A rough estimation about the market size, because you are a company. So.
Yeah. Well, for me, it would be difficult to know like estimates of the market. What I can tell you are the numbers that I was mentioning before, like 60% of the world population have some brain disorders, which can be of very different origins. Oops. And 20% of people above 50 are already at some stage of a cognitive decline process. So this is a world level problem. So the market is huge. And the problem is that products until now were very expensive to be acquired by normal people. Like you as an individual, is very difficult that can afford a neurotechnology system that costs, I don't know, 20,000. But lowering the costs, for instance, by using conductive textiles, will allow to get products that are easier to adopt by everyone.
Thank you.
But it is, sorry, just to finish, it's obviously good solutions for this would be that the national health systems can offer this kind of solutions, and you don't need to buy the system yourself, but you can be getting it as an ambulatory ECG when you have a heart monitoring, for instance.
Okay, thank you very much. I don't see any other question here. So from my side, again, about the power consumption of this kind of wearable devices. So my question is, I guess it would be low power. And besides, are you using, are they self-powered? Are you using a battery for the power supply? Or
yes, our systems are using a battery, and yeah, of course, that was one of our constraints. When we need to monitor sleep, we need at least 10 hours of autonomy, because we cannot have the person being monitored and having a cable that goes from the headband to the plug. So we needed to include a battery that at least lasts for 10 hours. Yeah, that was not a problem. So with the small size batteries that we have nowadays, it's enough.
okay, thank you. One last question from my side, at least. I still cannot see any other in the chat. So about the data analysis, all this data that are collected, I guess you do the data analysis in the cloud, or do you have any microcontroller or some data processing engine on the wearable, or you send them through the cloud?
We have both approaches. So for approaches like the one that I was telling about stimulation, we can process and provide feedback within the amplifier, the box that we have there. But for diagnostics, for the devices that we send home, we have also implemented a cloud solution that uploads the data automatically. And then the specialist can see the results there and make a more informed decision.
Okay, thank you very much, Eduardo.
Thank you.
So I think I cannot see any other question in the chat. So I would like to thank you for your participation and the acceptance of our invitation.
It was my pleasure.
This is the last webinar for today. So I would like to thank all the applicants, all the audience and the applicants. And let's meet again tomorrow at the same hour. I think it's 11 CET for the second round of webinars. Thank you very much, everybody.
Thank you.
Bye. 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 Bye, Eduardo. Bye.